Hello everybody and welcome to our physics engine creation videos. So we're creating a physics engine from scratch and so far it's been going really well. We have all of our collision responses working. And let's take a look at our program looked like last time we left off on our previous video. Today I'd like to start working on realistic physics and collision responses. And so by the end of today's video, we should have something that looks like this. And you can see it's actually starting to look more like a real physics engine, right? Before, our application looked more like a collision detection tool. But after this video, it should resemble a real physics engine as we have realistic responses to our collisions. So let's go ahead and get started with realistic physics and collision response. Okay, so now if we're going to have some realistic physics, the first thing I want to do is I want to be able to apply forces to the bodies. Okay, so first of all, I want to make a vector inside of our body class, and I'm going to call this a force vector. Okay, and this is going to be a direction and a magnitude of a force that we want to be able to apply to the body. And eventually, maybe I want to make this a list of forces, and we can apply lots of different forces and just run through the list and apply all the forces to the body every step. For now, let's keep it a little bit more simple. I'm not exactly sure what that's going to look like in the future, but I'm going to make it simple enough with just a single force right now anyways. Okay, so now that we have a force available, let me go ahead and define that real quick inside of our constructor for the body. And the force is just going to be 0 for now. Okay, so now we're going to scroll down here to the step. And every time we step, you can see we're incrementing the position and the rotation every step by the velocity. And now we're going to start working on acceleration. So just like the position is incremented by the velocity over time, velocity can be incremented by an acceleration over time as well. And let's go ahead and do that here. So we're just going to increment the velocity by the force, and that'll be on a per time basis, which is per second as well. All right, so that should allow us to apply a force. Let's scroll down here, and I want to make a function that will allow us to add a force. Let's call this apply force, I think, or maybe add force. Well, I'll start with add force for now, and yeah, maybe that will change that later, but it's just going to be a vector that we're going to pass in, and we'll just set the force equal to the amount. Okay, so I think we're almost done with that. The only other thing is once we want to go back up to the step for the body. Once we've applied the force, at the end of this step, I want to set the forces back to 0, or I want to set the force value back to 0. Okay, and I think that's everything we need inside of this, inside the body class. So let's go back to the game class and let's see if I can actually control the, let's see if I can control one of the bodies by using forces instead of just manually pushing the body along. Okay, so here we are back in our update function inside the game class. This is the point down here where we are just kind of manually moving by a velocity. So instead of moving by a velocity, I want to move by a force. And so I'm going to change this direction to a force direction. Okay, and then the speed, I'm going to change this to a force magnitude. All right, and that's just the amount of force. So now we have an amount of force, we have a force direction, and if we combine them, we're going to get a force vector. Okay, and that's what I'm going to call this here, the force vector. And then this will be the force magnitude here. So we're getting the magnitude, the direction, we multiply them together. Now, the other thing is I don't want to change it based on time right here. So if you look right here, I'm calculating the force by getting the direction, the magnitude, and then I'm multiplying it by the amount of elapsed seconds. And I don't want this to be in seconds right now. Okay, so I'm going to take that out because we're going to adjust it to be on a per second basis once we get back into the body class. And that's why in the body class right here, I took the force and I multiplied it by the time step. Now, instead of moving by a velocity, let's tell it that we want to apply add a force, and we'll just pass in the force we want to add. Okay, so let me just run this and see if it does what I'm thinking it'll do. Okay, there we go. And you can see it's kind of accelerating. As I press the up arrow key, it gives it a force upwards, and then to the left, you can see the acceleration. Perfect. Yeah, that looks good, actually. Okay, all right, so now that I can apply forces, what I'd like to do is now react in a realistic manner. So let's go back to the flat world. Here we are inside of our collision step. And we're going to add a function here. And this function is going to resolve the collision in a realistic manner. So here's collide. Right above collide, let's go ahead and make a function. I'm going to call this resolve collision. And then we just need to pass in all of, basically all the stuff we got out of the collide function. So the bodies, the normal, and the depth. Okay, so now that we have that, let's start talking about physics. All right. The way we're going to do this is we're going to resolve collisions by applying impulses. And you can think of impulses as a really quick adjustment to a velocity to make objects move apart in a realistic manner. I've got an article here. In fact, this is a series of articles that was written by Chris Hecker, I think is his name. Yes, here it is here. So by Chris Hecker, he has these articles right here on physics and rigid body dynamics and collision response and all these really good articles. They were written in 96 and 1996, 1997. And they really are the basis for what I'm doing here with this engine. Really great articles, probably the best I've seen as far as the balance between being able to present a relatively complex subject and learn how to do something like physics simulations, but in a relatively simple manner. And it's written really well. So I would suggest that you take a look at these articles. And this is the one we're going to use today. It's a collision response. And he goes through here and talks about all the different things that you would need to do to get a realistic collision response using impulses. Okay. And so basically, as I scroll down here, these are kind of the formulas that we're going to start with here. We have the resulting vector 2. So v2 is the resulting vector, is equal to the initial vector, or vector 1, plus j. And j is actually the magnitude of the impulse. So it's the amount of impulse that we want to apply to make sure these objects react in a physically correct manner. So j is the amount of impulse we want to provide. We divide it by the mass of the object and then multiply it by the normal of the collision. And then that's for the first object. For the second object, the velocity is now equal to the initial velocity minus, instead of adding, we're going to subtract the magnitude times the normal divided by the mass. So let's go ahead, and I'm just going to write that part in our code. Oh, and actually, we don't have access to the linear velocity, so I need to find some way. Let's go to our body class, and let's find some way of actually allowing us to adjust the... Okay, so what I'm going to do is I'm going to make a property here. I'm going to call this the linear velocity. Okay, and I want to be able to publicly get the linear velocity. So I want anybody who has access to the body to be able to get the velocity, but I only want to be able to set the velocity if you are inside the engine itself. So for getter, we're just going to return the linear velocity. And then we're going to have an internal set. And what that'll do is it'll make it so we can set the linear velocity inside the engine itself. But anybody who wants to can get the current linear velocity. Okay, all right, so now that we can do that, back in our world class, here's where we are resolving the collision. So let's get the linear velocity. We're going to increment the linear velocity. Okay, and let's go back to the article just so I can get this right. So we're going to increment it by a j magnitude, which is the impulse magnitude, divided by the mass of the object times the normal. So we're going to do j divided by, let's see, this is the body A mass, and then multiply it by the normal. Okay, and then body B is going to be the same thing except for the opposite. So now we're going to decrement the velocity by j divided by the body B mass, and then times the normal. Okay, and there we are. That is it. The only thing that's left to do is to figure out what j is. Okay, so let's go back up here. Let's make a value j, set it to 0, or actually I don't need to set it to anything yet. Let's just go back to the article and let's see what j needs to be. Okay, so if we scroll through the article here, he kind of talks about how you derive the formula for getting j, or the amount of the magnitude of the impulse. And here is actually the final equation. Okay, I say final equation because this is the final equation of what we're going to use today. There is another equation. Eventually, we're going to get into rotation and how colliding objects and how to rotate them realistically based on their collision and all of that. But for now, we're just going to disregard rotation and we're going to disregard friction. And we'll have to work on those at a later time. For now, let's just get this version working. Okay, so here's the actual formula. And what it says is that you have a numerator, which is the top part up here. And E is the restitution. V is the relative velocity. So that's the relative velocity of the two objects. And you get that by subtracting the two objects' velocities. And then this symbol right here, this dot, is actually the dot product. Okay, that between the velocity, the relative velocity, and the normal. N is the normal. And then this dot is the dot product. Okay, so we have E for the restitution, we have the relative velocity, we have the dot product, and we have the normals, and then we have the mass of A and the mass of B. Now, the other thing is over here, we have the N dot N, and that's something that we can, that for our engine, we don't need to put in there, because when you dot a vector by itself, you're going to get the magnitude of the vector squared, and our normals are actually already normalized. So it's basically going to be a magnitude of 1. And when you square 1, it's just 1. And so we're basically just multiplying 1 by 1 right there. And so it's not even necessary to compute that part. Okay, so we don't need to do that n dot n part, but the rest of it we do need to add in there. So let's go ahead and see if we can put this into our engine. So J, let's do the numerator first. So it's going to be a -1 minus the restitution. And we don't actually have the restitution, so that's another thing we have to compute. Let's go back up here and let's find out where the restitution is. And for the restitution, I'm just going to use the minimum of the restitution of the two bodies. Okay, so whichever body has the lowest restitution, that's the one I'm going to use. Okay, there's our restitution, nice and simple. Okay, now we're multiplying by the relative velocity. All right, so the relative velocity, we need to calculate that as well. Let's go back up here to the top. Okay, and that's just going to be the velocity of the two bodies, one subtracted from the other. Oh, let's see, I think, let's do body B linear velocity, and we'll subtract body A linear velocity. I think that's the way we want to do it, the order, because as far as my engine's concerned, I'm always pushing body B outside of collision with body A, so I think that's the order. We'll test that and we'll see if it works correctly. Okay, so now that we have the relative velocity, we can put that in here, and then we need to take the dot product of the relative velocity with the normal. Okay, so we'll just bring in our math library right here and take the dot product with the normal. Okay, so that's the whole numerator right there. Now let's do the denominator. So J is going to be divided by, all right, so for the denominator, J is divided by, and let me go back to the article here. So remember the n dot n we can ignore because that's just going to end up being 1 anyways. So we're going to take the 1 over the mass of A plus 1 over the mass of B. Okay, so here let's just do 1 divided by the body A mass, and then we'll add that to 1 divided by body B mass. And I think that is everything we needed to do. Now it's giving me an error down here, and I think I know why. So it's telling me the multiplication operator cannot be applied between type float and type flat vector. And so let's go back to our flat vector class. The reason it can't do that is because I did write this multiplication operator, but I also need to write the reverse. If you look at the parameters here, it has a flat vector times a scalar. And I also need to write one that has the reverse where I can put a scalar times a flat vector. So I'm just going to copy this. Okay, and we're just going to reverse these parameters. And then once I go back, that should get rid of the error. Okay, so the error is gone. And now I think we have everything we need to resolve our collision in a physically accurate way. And I may have to reverse some of these signs. In fact, looking at this, I think we're going to increment B and decrement A. And the reason I'm doing that opposite of the way they did in the article. So if you go to the article, the way he did it here, he incremented A by the impulse and decremented B by the impulse. And so the issue with mine is that I'm resolving the collision kind of in opposite direction. I think with his engine, he was always pulling A out of B, which is probably more standard. So I'm always pushing body B out of body A, which might be a more non-standard way of doing it. But so some of the signs that I write might have to be reversed. But let's just try this and see if I got it right. And all we have to do now is inside of our collision step. Okay, so we're right here. We found a collision. We've actually moved the bodies apart right here with these two lines. And then we're going to resolve the collision. Okay, and all we have to do is pass in all the information. Okay, and I think if I did that right, if I think if all the signs and everything are correct, now eventually what I'd like to do is instead of passing all of this information around just like this, you can kind of see how we're just passing it all through all 4 of these things. I'd like to create a collision manifold, and that'll just contain all of this information. And then we can just pass the manifold to any function that needs it. All right, so actually, I would like to give that a try. Let's go ahead and run this and just see what happens. Oh, and I'm actually pushing a button, but nothing's happening. And I think the reason is I've got a problem with my, so I need to go back to the flat body. There was one thing I need to change. I've got a bug in the code. Okay, yeah, every time we're stepping here, I think what I need to do is tell it that I need the transform update to be required. Let's just update this flag right here. So every time we step, I think I need to make this happen. And actually, now that I look at it, if I do this in the step function, I'm not sure if I need to do it here because I'm updating it here in the step. I'm not sure if I need to update it inside each one of these. That's something I'll have to look at later. Let's just see if that resolved the issue. Okay, so there I am. I'm moving the circle, and let's just see if I can collide and see what happens. It looks almost right. Something isn't exactly right. You can see they're colliding, but it's almost like one of the... let me go back to the code. I think there's something... It almost looks physically correct, but it doesn't have quite the right feel to it. I'm not getting the right bounce, I guess I'm not getting the right collision restitution. I'm not getting the right impulse. Something's not quite right there. Oh, okay. All right, so let's just go back and look at the article. I think I might have written part of this equation wrong. In fact, looking at this, I think it's this part right here. So I wrote 1 minus the restitution, and I think that is wrong. So let's go look at the article. Yeah, and it's supposed to be 1 plus the restitution. Okay, so that makes sense. Let's go back and correct that. I think that's the only thing we're missing there. So change that, and let's see what happens. Yeah, okay, that looks really good. All right, so there we go. I'm applying a force to this object. It hits the other objects and they bounce off. And that looks really good, very realistic. The only thing that's not really realistic about it right now is that there's no rotation. So that part of it isn't there, but the way it feels very realistic. So basically that's it. This is how you resolve collisions in a realistic manner if you have a normal and a depth value. So that's pretty much it for that function right now. Now it's going to get a little bit more complicated when we start adding things like rotation and friction, things like that. But that looks really good. So that is realistic collision resolution. Something real quick I want to do at the end of this video here is I just want to go back to the game class, and you can see when I run the program, when the objects hit, they go off the screen and they don't come back. So I'm going to make a function real quick that's just going to make everything wrap back around. Inside the game class, just at the bottom here, let's make a function. I'm going to call this wrap screen. And we're just going to loop through all the bodies, and let's make sure that they stay within the bounds of the screen. If they go off the edge, they're going to loop back to the other side. At the top here, let's go ahead and get the camera extents. All right, let's calculate the actual width of the view of our camera. Actually, this would be I'm going to call this the view width. Okay, and let's just test to see if the body has actually moved outside of the bounds of the camera. Okay, so if the body has moved off to the left too far, it'll move the body back to the right. So by the amount of the view width. So it's just going to wrap around to the other side. And I'm just going to do this 4 times, one for each of the one for each axis. Okay, and then these will be the view heights. So now what it's going to do is find out if the body has gone to the edge of the screen and off the screen, and then if it has, it's going to wrap it back around to the other side. All right, let's just test to see how that looks. Oh, and actually this needs to be moved to, not move. So change all these. Okay, so now that I've created the wrap screen function, let's go up to our update, and we'll just tell it we want to wrap the screen. And let's run that and see what happens. Okay, we'll just go up to the top. And there we go. Okay, so they'll just wrap around to the other side. That side works. Side works. Let's put a lot more bodies onto the scene. Okay, so we have at 10 now. Let's try 30 and see what happens. Okay, so here's the one I can move. Let's start bumping into everything. All right, that looks good. So that is realistic physics and collision response.